There are some students who tend to calculate distances in a vectors question by approaching it from the formulas perspective. We need to recognize that the formulas perspective, that means using the two formulas that are given to us here, for example, this formula here and this formula here, they are not going to provide us a consistent way in calculating distances, especially when we do know that in exams the situation can change. For example, like this is actually a little bit of a tweak from whatever that is given to us there, which is more commonly seen in our lecture notes. So what we need to, in order for us to achieve a more consistent way of calculating distances, is to try to approach it from a more geometrical perspective. And to approach it from a geometrical perspective, our strategy is to try to find our magic triangle, the triangle that we have been talking about so much every single time when we discuss about distances in vectors question. So for example, for a scenario that is like this, let's try to first find a magic triangle. A magic triangle will possess three things. Number one, it should be a right-angled triangle. Do we have such a triangle here? I think so, because I see a right angle here. So I believe that this is going to be the right-angled triangle. So this will be the first thing. The second thing will be we need to gather enough information about the hypotenuse of this right-angled triangle. Do we have that? In fact, we do, because this is vector B. So this distance here, which is the hypotenuse, this distance here is going to be modulus of B. So this is the second thing about the magic triangle. The third thing about the magic triangle that will make the triangle magical is the assignment, the allocation of theta. Because in this case here, there are two positions for us to assign theta. We can either assign theta here or assign theta here. If I were to just blindly follow whatever that is more familiar to me in my lecture notes, I could have probably assigned theta here, but we need to assign theta such that we will be able to make use of either the dot product or the cross product later. And the theta that is in the dot and cross product will always be the angle that is between two known vectors. So if I were to look at the scenario here, I know vector A and I know vector B. These are two vectors that are already given to us. So I'm going to assign theta here. So this is my third thing that will allow me to now say that this right-angled triangle here is that magic triangle that we have been looking for. So once we have fulfilled all the three conditions in order for us to say that a triangle that is in the scenario is a magic triangle, then it is time for us to calculate distances based on the geometrical perspective that we have gathered so far. So for this that we have here, we can imagine it to be a right-angled triangle, for example here, and we have angle theta and we have the hypotenuse r. So we want to find what is this length and what is this length with respect to r and theta. So for example, for this length over here, let me call it x. So I know that cosine theta is going to be adjacent over the hypotenuse. So x here is going to be r cosine theta. So let me rewrite this. This is r cosine theta. And I'm going to try to find this distance. Let me call this distance here y. And if I were to do a sine theta, then sine theta is going to be opposite y over the hypotenuse, which is r. This tells me that y here is going to be r sine theta. So let me replace this. This is r sine theta. So if the question or if the problem requires me to find this distance or this distance here from geometry, it is modulus of b cosine theta, and this distance here is modulus of b sine theta. Let's try to calculate for this distance, which is modulus of b cosine theta. But because we have chosen the place to put theta correctly, which is the angle that is between vector A and vector B, now I know this theta is going to be the same as the theta that is in A dot B, because A dot B will be modulus of A, modulus of B, cosine this theta, cosine theta. So if I were to look at this equation here, this equation actually does have modulus of B cosine theta, which we are trying to calculate. So if I were to just rearrange this such that I make modulus of b cosine theta the subject, we will have modulus of b cosine theta to be a dot b divided by modulus of a. And since we are calculating for distance, the distance will be modulus of a dot b divided by modulus of a. So this will be the distance, let's say distance 1, okay, which is this distance here. So now this is going to be modulus of a dot b divided by modulus of a. And if I were to just plant the vectors into the dot product, vector a and vector b into the dot product, we can then very easily calculate for the distance. How about this? I want to calculate this distance. Geometrically, we know this distance is modulus of b sine theta, and sine theta is cross product. And because of the place that we have chosen theta to be assigned, we know this theta is going to be, in this cross product equation, is going to be the angle that is between two known vectors, which is A and B. So now I can also quote this formula, modulus of A cross B. This is equal to modulus of A, modulus of B, sine theta. And we do see a modulus of B sine theta here. And by making it a subject, modulus of B sine theta, this is equal to modulus of A cross B divided by modulus of A. So now we know that this distance, let's say D2, this distance here, can also be calculated by doing a modulus of A cross B divided by modulus of A. So we have a modulus of A here. So in order for us to